Okay, so let's relate the frequency response here to time domain signals a little bit. I talked about the audible range, which is 20 hertz to 20 kilohertz, and so I'd like you to get a little bit of a visual picture of that. Professor Bacco, later in the course, is going to detail this quite well mathematically, but I think it'd be helpful for you to have a simple understanding of frequency response now. And so what I've done is I've picked the peerless transducer that we'll talk about a little bit later as well in the course. If we take a look at the frequency response, which is shown here with the curves in red and pink and black, let's zoom in here for a minute. The black curve is on axis, meaning straight on center with the speaker itself. A microphone placed in the room to make the measurement. And what I'd like to focus on, and I'm going to sketch here on it a bit. If you look at the lower x-axis, you'll see 10 hertz, 100 hertz, 1000 hertz, 10,000 hertz, and then on up here is 100,000. The audible range, and this is a logarithmic scale, so we're going to have the audible range is going to go up to 20 kilohertz, which corresponds to this line in here, and the audible range starts at around 20 hertz, which is here. Okay, and so you're going to see the frequency response of the speaker is going to frequently be displayed over this bandwidth. That's what we talk about in terms of bandwidth. And if you look at this particular speaker, on the left side over here, the left axis represented the sound pressure level in decibels, again a logarithmic scale. But this is if you look at the black curve here, you'll see that you start getting significant roll-off on axis here at what looks to be in this range around what do we have? 2, 3, 4, 5, 6, around 6 kilohertz. It's flat on axis, and then we start rolling off in response. So, this is a general indication of what the frequency response of this driver would be. And if you were going to really apply this in a speaker design, you might use it, from this range. And if you really care about the off-axis response, maybe you only plan on using this over this portion of the audible range, which is, on the order of 90 hertz up to, say, 2 kilohertz. Okay? So that's frequency response. And you'll see that, and there's a corresponding frequency down here on the x-axis for every amplitude of response that we have on the y-axis. All right, so let's move this around now, and let's relate this to time domain response. And what I want to do is I want to talk about the time domain response at 1000 hertz. Okay, so if we were to basically draw a line, just take a slice right out of the frequency response here at 1000 hertz, then we'd end up with a time domain signal that looked basically like what you see here. This is just a simple harmonic. As a matter of fact, each frequency is represented by a simple harmonic in the picture above. And so the key here is the amount of time it takes the wave to perfectly replicate itself. So this is one complete period of the wave. So the amount of time that it takes for the wave to complete a cycle is t. Okay, and that relates to the frequency as follows. The frequency is 1 divided by the period, or conversely, the period, the t here, is 1 divided by the frequency. So at 1000 hertz, the period is 1,000th of a second. Okay, if we had a time domain wave at 100 hertz, of course for the frequency corresponding to 100 hertz, it'd be a hundredth of a second. Okay, and so that's basically just relates to the time for the required for the wave to repeat itself. Now, one last thing with respect to frequency response: when you hear a signal in time, in actual fact, there will be many time domain signals superimposed on top of each other, and you hear them all at once. I mean, when you hear a signal in time domain, that's the way you hear it. When we look at the frequency response, basically what you're doing is looking at the amplitude response. In here, you'll look at the amplitude response at any given frequency. So it's as if we're taking a snapshot at a single frequency that allows us to look at the amplitude that would occur for the corresponding period in the time domain. Okay, so that's the relationship. This is helpful. Frequency response is a helpful way of looking at the characteristics of speakers, because you can see, in particular, or any given instrument, you can see areas where the roll-off occurs. The objective, obviously, is if we could make a perfect speaker, and let's just sketch that here. The objective in the end is if we could have a perfect speaker from 20 hertz right here all the way out to, sorry, right here, 20 kilohertz, we would have a flat frequency response. All right, and if we could have a speaker like that would represent sound, replicate sound over those frequencies equally, then it would be perfectly matched to our audible range.